actually indicates that when you add water, what happens to the new strength. And anytime you add water, you actually decreased the concentration because you've just added volume. Now, most of you, if you ever make orange juice at home and you take 1 can of frozen orange juice and you add water to it, is a best example of dilution. Now, in dilution, the formula that is needed to practice with is the formula that is written over here, which states that anytime you have a change in the concentration or the volume is going to equal to the new volume and the new concentration. So for example, if whether we're using percentages or whether we're using molarity, in both of them you take the products of the concentration and the volume are always going to be related, initial to diluted. So one is this part, let's say, is the initial and this is the final stage. Now in both of them you have 4 different things. You have, I'm going to go ahead and use the examples of M, but M1 would be your initial volume, M2 would be your change in initial molarity and change in molarity. V1 would be your initial volume and change in volume. So what we're saying is the initial molarity times the volume equals M2 over V2. So keeping that in mind, let's just try looking at some formulas over here. What volume of 2 molar HCl can be prepared by diluting 25 ml of 14% HCl? So first, again, always take the word problem, break it down to understand what is given to you. Here it's a percentage problem, so that's why we're using the term C's. And in a molar problem you would use M. So it's the same concept. So you have initial concentration, which is 14 M, final concentration is 2. The volume is 25 ml. So what is the new volume? Now in these problems you don't really have to worry about converting liters to milliliters, whichever one is required. So looking at this problem, we're trying to isolate for V2. So V2 would be V1 C1 divided by C2. This problem is similar to your gas laws and how we applied the algebra over there. So you're putting V1, which is 25 ml. You can see 14 ml is your C1 and your C2 is 2, and you divide that and you get your new volume, which would be the volume that would be added that means that you actually take 25 mLs and you add 175 ml, so the total volume is now 200 ml. Now these problems are usually used in labs in scenarios when you're actually trying to prepare a solution. So here is another problem. What is the percentage of a solution prepared by diluting 10 ml of 9% sodium hydroxide to 60 ml? So I'll take you to the next slide in which we have broken down each of the information. We're taking 10 ml as our given volume, and the final volume is 60 ml, as you can see over here. Let's just get rid of this. Okay, so coming back over here, so we have 60 ml, which is our final volume, 10 ml is the beginning. The initial concentration is C1, so what are we trying to isolate is for C2. Again, once you know how to use your algebra to get rid of the undesired factor, you can change the formula to the required way of isolating it. So we got rid of V2. Again, I'm repeating it. You do it on both sides. So your new equation is this. You plug in the value of C1, which is 9%, V1, which is 10 ml, and V2, which is 60 ml. This tells you that the new percentage is 1.5, and actually it makes sense, because if you take a 9% solution and it's 10 ml and your final volume is 60 ml, which means that you've just added 50 ml of water to it, the new percentage will be less than the beginning volume. We're almost getting to the end. Okay, dilutions in which we will do the same sort of problems, but you're using molarity in respect over here. So what is the molarity of a solution preparing a dilution of 1.8 of 0.6 molar to 0.54 liters? Again, these are given tables. You can see that these two are the volume, V1, V2, 0.6 molar is our initial. So what are we trying to find out is isolating it for M2. Same thing we did. The only difference is we're using the terms M instead of C, but it's M's representing the same factor. It's just that we're using molars, and we come up to 0.2 moles of this solution. Here is another problem very similar to the one I just did. What is the final volume of 0.15 of 1.8 molar potassium hydroxide? If I try to solve this one, you can see that M1 is given to us, and M1 is over here 1.8 M. Final molar solution is 0.3. Initial volume is 15. So what are we trying to find out is what is the change in the new volume. So once you calculate for the change in the new volume, you find out the new solution should be 90 ml. Now if you were actually to go ahead and prepare this solution, you would then notice that you have 15 ml to begin with. So how much water should be added? How much water would be added would be 90 ml minus 15 ml, and that would be 75 ml of water would be needed to make the solution from M1 to M2. Now we're almost at the end. The last two terms are mainly some terminology about some of these different terms. Solutions is a homogeneous mixture. On the other hand, colloids have medium-sized particles, and suspensions have large particles. So, for example, milk would be a colloid because we have medium-sized particle. It cannot be filtered, but can be separated by cell membranes. Milk, cheese, blood plasma, pearls are all examples of colloids. And suspensions are when you have larger particles that can be filtered and must be stirred to stay suspended. Blood platelets and muddy water are actually examples of suspension. Okay, this last slide is really important for biology purpose. Keeping in mind, let's look at the concept of osmosis. What is osmosis? Osmosis is the flow of the water from lower solid concentration into higher solute concentration. So for example, now the key word that I'm using is solute. So for example, if I have 5% sodium chloride solution on this side and 1% sodium chloride solution on the other side, water is going to move from the lower solute concentration. The key word here is solute. So don't get mixed up. This is the one that has lower solute. So water is going to go from this end to the other end. Level of solutions with a higher concentration rises. So now water will add more towards here. Now why is it so? Is because 1% solution means that there is 99% water and there is 95% water on this side. And water always moves from the higher concentration to lower concentration. So what will happen to this side of the solution? This side of the solution will then actually get larger, or it will be more. So keeping in mind, let's look at the three different scenarios that are shown over here. In this case, you can see that this cell is placed in a solution that has more water outside. So when you have actually more solutes outside, or more, so when you have more solutes and you have less water, same thing over here. So you can see what's going to happen in this way. In this case, water is going to leave from the inside to the outside. On the other hand, in this scenario, you can see water is coming from the outside to the in because there's more water outside than in. So when water moves this way, what happens to the cell? The cell's volume is expanding. It will eventually burst. In this scenario, because there's more water in than the outside, so the water is leaving the cell and the cell membrane shrinks. However, in an isotonic solution, there's no change in the flow of water. So make sure you know what isotonic, hypotonic, and hypertonic means. Iso means same osmotic pressure. Hypotonic is lower osmotic pressure. Osmotic pressure is the pressure of the solute particles dissolved in water, and it is equal to the pressure that prevents of additional water. Osmotic pressure is always measured with the amount of water. If you have same amount of water, then the osmotic pressure would be same. In a hypotonic solution, there's less osmotic pressure outside, and there is greater there's actually more osmotic pressure outside and less inside, so that's why water is coming this way. So this is something you will again review in biology classes as well, but it's important that you do understand hypertonic, isotonic, and hypotonic. Hypo means less, hyper is high, and iso means the same. These three will determine the flow of water. Again, I'm repeating, the flow of water is based on the definition, as a matter of fact, reads for the flow of water in respect to the solute concentration. And that's why some people usually get mixed up, because they think of water flowing from higher concentration to lower, but just correct. But it also, if you're expressing it in solute concentration, then it's lower solute to higher solute, or you can say from higher water concentration to lower. But the definition actually uses the terms of solute. And the other important thing for osmosis is that osmosis usually takes place when you have a membrane which is selective to certain particles, because if there was no semi-permeable membrane, it would just be a process of diffusion from higher end to the lower end. So it's the particle is moving through a barrier which is semi-permeable, which allows movement of certain molecules and not the other, and it usually allows the movement of water.